Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 56 of our synchronous machines chapter. So today we will be discussing about stable region of operation, synchronizing power and synchronizing torque. Okay, so before starting obviously all these topics, we had few questions. I gave you few questions as homework. So we will do those questions, right? And I will quickly summarize whatever we have learned. Okay, regarding the power. I have already summarized regarding the uh, that that tan xi and EF magnitude of EF. I will summarize regarding the power, right? Comparing the cylindrical pole rotor and the salient pole rotor. Okay, so let's solve this first question. Given like a three phase 50 hertz, so F is 50. Salient pole, so salient pole is there, so just be careful, right? And unfortunately, that active power formula you have to remember. Okay, uh, has per unit per phase direct axis reactance XD. That is equals to 0.8 pu, and a per phase quadrature reactance xq is 0.6. You're observing, right? Xq is lower than xd, and that is generally the case. Xd will always be higher than xq. Okay, practically resistance of the machine is negligible, so Ra is negligible. You are safe. It is drawing full load current at 0.8 power factor. So full load current, what will be Ia? Ia will be 1 pu. Full load means rated current. So that means it is 1 pu. In per unit, it is 1 pu. And your power factor cos phi, it is already in per unit. It is 0.8 leading. Okay, and terminal voltage, of course, Vt will be 1 pu. Now what they are asking me the per phase induced voltage. Very simple, right? What is the formula for per phase induced voltage? If you want to remember, you can remember it. Okay, the formula, what was the formula? This was the formula, right? So method 1 is using the formula. I think it will be better if you do it with formula, otherwise. Okay, method 2 is there, but you have to calculate I, Q and I, D. That will be difficult for you to calculate. Yeah, that will be difficult. You have to use formula only. Other than that, how can you find out? You can find out tan xi, but again you have to use the formula only. That is also true. Okay, so the formula, if you remember, the formula was E. Like only, I think there is only one method. Other method will not work actually. Like it will work. It is basically deriving the formula. That will take you more time, right? If the ID current, IQ current were given, then it would have been easy for you to solve. Okay, so this was, if you remember, under root here, it is a leading load. Leading load means it is negative and it is a motor. It is a motor, right? So motor formula here, it will be V cos theta minus, it will be minus IRA. RA is 0, so IR will be this. Okay, plus V sin theta plus IA xq. So this, right, you have to unfortunately remember. Of course you can derive it, right? Like just like how I had derived, you can obviously derive it, there is no problem, but it will take time. That's the only thing, it will take time, right? So this square. So I know everything, right? I know what is Ia, it is 1 pu. I know what is V is 1. Sin theta, I know it is 0.8 leading. Already sin is taken, sorry, cos phi is 0.8. So sin is already taken care of. So this will be under root 0.8 whole square plus 0.6, right? V sin theta will be 0.6 whole square, and of course I have Ia is 1 pu, xq is 0.6, 0.6 whole square. So this will be 0.8 whole square plus 1.2 whole square. So 0.8 whole square plus 1.2 whole square whole under root. So E comes out to be 1.442. Okay, so this is the value of your E basically is 1.4402. Okay, so 1.442 per unit. Okay, so this will be the answer of this question. Now there is a bit of controversy I can hear, like, because answer key has given as 1.6. I don't know, according to me 1.44 should be answer. You can let me know your counterpoints. According to me this should be the answer, right? So yeah, let's solve the next question. In a salient pole synchronous motor, the developed reluctance torque attains its maximum value when? So this kind of simple questions get asked, right? What, remember, what is the reluctance torque proportional to? Like with respect to the delta, it is sine of 2 delta, right? So when will this attain maximum? When, if everything else is constant. So when sine 90, the angle inside the sine function is 90, then it will attain maximum. That means your 2 delta, that means your 2 delta, 2 delta, right, has to be 90. That means your delta has to be 45 degrees. So at 45 degrees, it will attain maximum reluctance torque. Okay, reluctance torque will attain maximum value when angle will be 45 degrees. Okay, now let's before coming to this, right, I want to have a quick discussion regarding the power formulas. So we for a cylindrical pull rotor. So Vt is my reference, right? So Vt is my reference, so Vt will be here. This is my Vt, okay? And this equation we know, right? For a generator, if I have a generator, it is simply Jxs. This terminal voltage is Vt angle 0. This is EF angle delta, right? And this is current Ia angle theta. Okay, so this is Vt, this will be Ia, that is lagging theta, and my EF will be somewhere around here. This is my delta. EF will be leading by Vt by delta, and your IAJXS, right? Basically your equation will be what? E will be equals to, EF will be equals to Vt plus J IAXS. So plus J, so I have to rotate this by plus 90. Okay, so yeah, if I want to make it totally equal, right, so basically what will happen, this will lie somewhere around here. Now what is the active power transferred? What is the power transfer? That is like this, right? We have already derived. I'm just deriving it in a different way. I am just deriving it in a different way. Okay, how can I derive it in a different way? That is what I am trying to get at. Okay, so this will be Vt Ia cos theta, because whatever power it is delivering, same power it will receive, because this does not have any lossy component. So if I break this, this is what, this is my Ji, or if I just write the magnitude IAXS. Okay, now if this is theta, what will be this angle? So if this is theta, that means this is theta, right? This is 90, this whole angle is 90, right? This whole angle is 90 because I have just drawn 90 parallel to this. So this angle will be what? This angle will be 90 minus theta, right? This angle will be 90 minus theta because this whole angle is 90, right? This is theta, correct? Because this is just parallel. This angle will be 90 minus theta. So this angle will be theta. Okay, this, because this is 90, right? Okay, Now I will break this down into two components. So my basically what I can say, one of the component, like I'm deriving it in a different manner, that my Vt, sorry, Ef cos delta along this, and Ef cos delta will be equals to Vt plus Iaxs sin theta. Ef cos delta will be equals to Vt plus Iaxs sin theta. Okay, and what about the other component? So Vt does not have any other component, right? So Ef sin delta will be what? Ef sin delta will be, so this is Ef cos delta. Ef sin delta will be perpendicular to this somewhere here, right? Sin delta will be perpendicular to this here. So what is this component? This cos Ixs cos theta. So Ixs cos theta is along this component, and Ef cos sin delta is along the same component. So Ef sin delta is equals to Iaxs cos theta. So from here I can replace my Ia cos theta to Ef sin delta, right? So this actually we had derived previously, but I am doing it in a different approach, okay, with phasors. So I can write my Ia cos theta will be equals to Ef by Xs sin delta. So from here I can directly derive the power formula. The power formula. The power formula will be basically P will be equals to Ef Vt by Xs sin of delta. Okay, that is what my P is equals to. Okay, so that is what my power is equals to. Now what about reactive power? So reactive power, right? Again, what is my Q? Q is Vt Ia sin theta. So what is Ia sin theta? So Ia sin theta I can derive from here. So Ia sin theta will be equals to Ef cos delta minus Vt divided by Xs. Okay, so if I replace this Ia sin theta here, right, what will I get? So I will get basically my Q will be Vt into Ef cos delta, Vt by Xs into Ef cos delta minus Vt. Okay, that is what my Q is equals to. Okay, now this, right, actually is very important term. It is basically telling me that my reactive power is proportional to the voltage difference, roughly, right? If delta is very small, it is roughly equals to the voltage difference in the line. This will be used in power system. Okay, so from this we can understand that your reactive power is proportional to the voltage difference across the line. So if this end voltage is Ef, this end voltage is Vt, right? So voltage difference, higher the voltage difference, higher the reactive power. Okay, so this is what this equation tells me, and this equation tells me basically the active power. Okay, so this is the expression for reactive and active power, right, in case of a cylindrical pole motor, and for a salient pole motor, this was the expression for a active power, right? This is the per phase expression. So I forgot to derive, like previous lecture was already long. I forgot to derive the expression for the what do you say, reactive power, right, for a salient pole machine. So let me take a new page. Reactive power for salient pole machine. Okay, so reactive power for salient pole machine. So power basically, power for salient pole machine, right? This was the active power. What about the reactive power? So reactive power, again I have to obviously bring the phasor diagram and everything, because reactive power will be what, Ia sine of theta, right? Again we have to derive it. Okay, it will take us time. So I will copy this phasor diagram, everything, right? Because again I have to derive the reactive power. Actually we had already written this thing, so I will copy this. Actually this will be required. Actually this much is enough, I guess. ID, and if I just get ID and IQ, that will be enough, I guess. I will see what I can do. So before this, right, before this is a derivation part, this is a conclusion part basically. Before this I want to derive the reactive power. Otherwise, like I want all the 4 pages to include the formulas basically. So this was the derivation for the active power, right? I will just copy and paste again the ID and IQ part. That will be useful to us. I will use it. Okay, so uh, my RA is equals to 0. RA is equals to 0. What I can say is uh, uh, this is my VT, right? So what will be my reactive power output? Reactive power output. Reactive power output. We want to find out the reactive power output from the okay, one thing I forgot to mention here actually. Here, right, this reactive power that I just derived, where is it? Here, right, I derived the reactive power. This kind of is this will be, this is at the terminal, but what is the reactive power sent from the generator? Actually I want to find out reactive power sent from the generator. It does not matter what. Okay, what is the receiving and reactive power? That is what we are calculating. That's fine. We will only calculate the receiving and reactive power. Okay, so this, right, this was the formula for power. Now I want to write the reactive power. So reactive power will be what? Again reactive power due to IQ and reactive power due to the direct axis current, right? Two components of reactive power will be there. How? So ID is here, IQ is here. So if I again make two components of VT cos delta, it is out of phase to ID, right? So ID into VT cos delta will give me one of the reactive power. So ID into VT cos delta, right? So ID into, this will be ID. This will just change to ID. That's it. Okay, I hope you are understanding. So it is basically VT IQ into sine of theta q. Okay, you can see from the phasor diagram, and this will be VT ID into sine of theta d, and this will be this only, basically the out of phase component. So if ID is here, here is my VT cos delta, here is my VT cos delta. So ID is here, right? So my reactive power will be VT cos delta. So because this VT cos delta is along this line into the out of phase component current, that is ID. Okay, same here, VT sin delta, that is along this line, and into the out of phase component, that is IQ. That will give me the reactive power. Okay, that will give me the reactive power. Now so this already we have derived in the previous lecture, what is ID and IQ. So I will just replace it in this equation. I will just replace it, right? So this will become VT cos delta into ID. This time it will not be IQ anymore, this will be ID. So ID is here. Okay, so ID will come here actually. That is okay, that is very easy. So ID will come here and IQ will come there. That's it. Okay, so from here what can we understand is VT is anyways common. VT I can take common, anything else I can do, nothing much like this formula is not important, like this much portion is only important. This is Q. Remember, this is Q at the terminals, okay, at the terminals, because this generator will send some other reactive power because this has a reactance, right? So this will consume some reactive power. Then after removing that, how much am I receiving at the terminal? That is what this is calculation, because it is Vt into sine theta. Remember, terminal voltage. Okay, so don't worry, this will not be asked actually. So now, what is the important portion here to understand is that, again if you observe one thing, that okay, let me do this like this. Some similar formula with respect to active power will come, but you don't need to remember it. But again, if you observe, my reactive power is proportional to delta V. Whatever is the delta V here, that is what my reactive power is proportional to, right? So same thing you are observing, that reactive power will always be proportional to delta V. So this is the formula for the reactive power of a saline pole machine. Now you don't need to remember it. Okay, active power you can remember, and even though if you forget the active power as well, you can draw this phasor diagram. So this phasor diagram is the most important portion, right? How am I drawing this phasor diagram? So you go back to the previous lecture, again see how have I derived it. This is the most important part. If you are able to understand this phasor diagram, then you will be able to derive the expression for active power and reactive power. Active power you remember, reactive power you derive. That will be the best portion. So in this 4 slides, okay, I have basically derive the expression for active power and reactive power. So I want to give a question to you, basically this question: can you find out the expression for active power transferred from the salient pole generator? Okay, if it is a salient pole generator, and what will be the active power transfer? If remember, currently the XD is the direct axis reactance, that is not shown, here, that is internal to the generator. XQ is the quadrature axis reactance. And if my line has a star network like this, how will you solve it? Okay, very interesting question. So one more key point, if you want to understand, if you make here, right, in this equation, if you make basically x q equals to xd equals to xs, then you will see that basically you will get the previous expression. So this will become xq xd, right? So this will be minus vt square cos square delta, and this will be vt square sine square delta. Okay, minus is there. This will be ef vt cos delta by x. Okay, here what was the expression for q? Here it was ef cos delta minus vt square by x. Okay, somewhere something wrong I have done. P plus actually. Okay, here is the id current. Okay, one more. Okay, I think one more mess up I have done here. One more interesting mess up I have done. So here, if you observe, right, this Vt, this is my Vt cos delta, and Id is lagging. So it's a lagging reactive power. So this one is a lagging reactive power, right? Okay, one mess up I had done. This is a lagging reactive power. So this will be positive only, no problem. But this one, right, if you see, okay, this will be I guess, so this will be IQ, right? So Vt cos delta is here. So this will be ID only. Okay, this will be ID only. Okay, no, okay, let me, Vt sine delta is here. So this actually, again, I have done some sort of into ID. Okay, and this is into IQ. Anything mess up I have done? So Vt cos delta is here. It should be ID. Vt cos delta ID, yes. Vt cos delta ID. That is fine. Yeah, Vt cos delta ID. That is fine. Vt sine delta IQ. This should be IQ actually. I forgot to remove it at that point of time. This should be IQ. I forgot to change it. Okay. So here, if you observe that my Vt sine delta is here and IQ is here. So IQ is leading. So it's a leading reactive power, right? Leading. So I cannot add it. That's my fault, right? Again, I was making a mistake. So we assume, according to our notation, lagging reactive power as positive. So this has to be negative. This has to be negative. Very important point. So previously, if you observe here in this derivation, right, my this, right, my current was always lagging. So we will always get a lagging reactive power. Anyways, there was only one reactive power, so everything was simple. But here I forgot to mention that this will be negative because it is a leading reactive power, and leading reactive power will be negative according to our notation. Okay, so this will be actually negative. I'm really sorry, this will be negative. Now if I make xq equals to xd equals to xs, then this will become vt square cos square delta. This will be minus vt square sin square delta. So if I take minus vt square common, it will be sin square delta plus cos square delta, that will be 1 by xd. Okay, by x, basically that is already present over here, vt square by xs, right, minus. And what about this term? This is what, ef into vt cos delta by x, that is what is present over here, ef into vt cos delta by x. So same, right, if you make your xd equals to xq, you will get back this value. If you are able to remember this formula, well and good, otherwise you derive it. Okay, and be careful regarding this, sign. I was also making the mistake. So it's a leading reactive power, that's why it is a negative. Okay, so every concept will be cleared here. Okay, so yeah, these are the formulas basically. Now can you derive the power that will be delivered? So in this kind of cases, right, it might seem very difficult, you will solve with networks, but actually it is very easy. For active power, you just need to convert this circuit, right, like this. And here I will have a terminal voltage Vt angle 0. Here I will have whatever voltage EF angle delta. You just need the potential across the reactance, that is connecting the receiving end and sending end, that's it. Okay, and you don't care whatever is the reactance over here, you don't care about it, because no active power will not flow through the reactance, right? Active power will flow from here to there, right? So P will flow from here to there. So whenever you are in a power system or something, right, this will be very helpful. So if you have to calculate active power between, this will be helpful in power systems as well, between sending end and receiving end, just find equivalent reactance between sending and receiving end. Okay, so basically you have to convert this circuit in this format. Can I convert it? Yes, I can convert this whole thing, right, into delta. It is in star, so basically I will have here EF angle delta, and if I convert it into delta, right, this will become like star to delta, so it's basically division. I have also forgotten the formula. I think it's by 3, star to delta I think it's by 3 if I remember it correctly, right? Star to delta is by 3. Where is the delta? Okay, yeah, by 3. Yeah, I also have I also have my own technique, so it is by 3, so this will become XL by 3. This will become XL by 3, and this will be Vt angle 0. Okay, so now can you find it out? Now can you find out the expression? Now it is simple, right? So basically my power expression, right, will be this. Remember, whatever is the equivalent resistance from this point to this point, that is the most important portion. Due to that only the power will be there. Okay, due to that only the power will be there. So basically your xd will become xd dash will become xd plus xl by 3. Why it becomes, why we added, I have already discussed. Leakage reactance same, right? Your xq dash will become xq. Okay, just hold on. No, this is wrong, this is wrong. This formula actually, sorry, this question, right? Active power transfer for both, for from cylindrical, from the cylindrical pole generator and saline pole generator. Okay, so yeah, so this is the part 1 for cylindrical. Okay, for part 1 for cylindrical it will be very easy, right? For cylindrical, if no excess is given to you, like, then this is the line, basically this is the formula, right? The formula for power transfer will be P will be equals to EF. Now previously we had only this thing, right? Excess, then this VT. So this excess is actually is like this. Excess is actually this only. Okay, so this will be EF VT by XL by 3 into sine delta. Okay, this was for the cylindrical pole rotor. What about the salient? For salient, right, what you will do, you will find out the equivalent reactance. You can do the same for, like, okay, I will tell you. If let's say excess is not given to you, so like this has two cases, excess not given. If excess is not given, you will assume that they are talking about this synchronous reactance only. This is the synchronous reactance. Then you will write your power expression like this. If excess is given, second part, if excess is given, then it's difficult. Then what you have to do is, you will have your E here, you will have your excess over here, and then you will have all these things, right? This XL by 3, this also will be there, XL by 3, this also will be there, XL by 3. Ultimately I will have here VT. So now how will you solve it? So now what you will do is, you will simply find out the X equivalent from here. That's it. If you are able to find out the X equivalent, you will just replace this network. Okay, you will not find out X equivalent, you will find out XTH and VTH. That will be difficult. Okay, that will be actually very difficult. Yes, XTH is easy to find out, but how about VTH? VTH is also easy to find out. Yeah, then, like, unfortunately then you have to find out XTH and VTH, otherwise you will not be able to find out the value of, like, if excess is not given, then you have to assume that, okay, this is like they're talking the power like this. Okay, they're not like, excess is not given, so assumption is this is acting as a synchronous reactance. This is acting as a synchronous reactance. Okay, excess is 0 ideally here. Now here, if excess is given, then you have to find out XTH VTH here, and then you can solve it, right? Then you can solve it. So how XTH is very easy. XTH is very easy, right? So simply, this is short circuit, so this is simply short circuit, this path is gone. So here I have XL by 3, here I have XL by 3. So two XL by 3 are in parallel, so XTH will be XL by 6. XL by 6. Okay, XL by 6. Now what I can say is, yeah, now what about VTH? So VTH, right, will be again, this will be open circuit, right? Or sorry, VTH will be again, I have to find out VTH, right? So if I have to find out VTH with respect to VTM, open circuit voltage, because I'm finding VTH from here, open circuit voltage from here, right? So if I'm finding out open circuit voltage here, what will be the open circuit voltage that is at, okay, that is actually difficult for me to find out, right? Because here I have VT angle 0. So basically, if I have to find out the open circuit voltage, yeah, I have to find out the open circuit voltage. So this point is open, right? And here I have XL by 3, XL by 3, and this node is VT angle 0. So this node is open, right? So this will be what? This will be VT by 2 basically. It is open circuit voltage, VT by 2. Okay, simply VT by 2, because it is acting as a voltage divider, because this point is open circuit, right? This point is open circuit. I'm just calculating the VTH from here, open circuit voltage. If this point is open circuit, that means here no current is flowing. So this point is basically VT by 2. That's it. So now you will replace your circuit like this. So this will become XS. This will be XL by 6. And here I will have VTH, that is VT by 2 angle 0. And here I will have my E angle delta. Okay, so that's how you will solve. No, trust me, nobody will solve, like nobody will explain this, nobody will take this question even. Okay, but I am expecting a question something similar to come like this. In case of a salient pole, what you will do, XD and XQ is given, right? So this portion will be same, calculation of VTH and XTH, this portion will be same. What you have to do is, this will be same, right? Your equivalent. So what you will do, you get your XTH, right? XTH. So you will add your XTH. You will add your XTH, because you will change the circuit. Like this will be my armature reaction XAR of the salient pole rotor. This will be my EF angle delta. This will be my open circuit voltage. Open circuit voltage will not change. This will be VT by 2 only, and this will be my leakage reactance XL divided by 3. And you know, not leakage, sorry, line reactance XL divided by 3 and VT divided by 2. And you know that in case of salient pole, you add the leakage reactance to both the XD and XQ. So same thing I will do here. I will add with XD dash. It will be basically XD plus XL divided by 3, and XQ dash will be XQ plus XL divided by 3, and then you just simply put this in the formula of the power. That's it. Okay, you just put the formula in the power, so you will get the answer. And remember, here VT is VT by 2. So this will be, so here did I solve it? So here what will be the power? So power here will be EF VT divided by 2 divided by XL divided by 6 into XL plus XS divided by 6 into sine of delta. This will be the power. Okay. Okay. And here here the power will be this simply XL divided by 3, and here what will be the power? But here I will have to replace VT by VT by 2, right? Everywhere I will have to replace VT to VT divided by 2. This will also be replaced with VT divided by 2. Okay. This XD will become now XD plus XL divided by 3. Here also, right, you will replace like this. I will not write it. So XD will become XD dash, otherwise it will take too much amount of space. XD will become XD dash, XQ will become XQ dash, XD dash will be XD will become XD dash. That's it. Other things will be same. Okay. So I hope you now it is clear that how will you write the power expression if I have a weird circuit. Okay, I'm expecting in the future years this question to come, yet something like this have not been asked, because it is not that difficult to think, but it is tricky and most students will ignore this concept. Okay, no one generally teaches this concept, right? So that's why I thought of explaining it. Okay, so these are the things basically. So now let's come to the stable region of operations for synchronous machines. What are the stable region of operations? Okay, so let me first start off with the most basic equation: cylindrical pole. Motor we can start. Motor, generator does not matter. Okay, I can start with generator as well, does not matter, because active power expression will be same, it will not change because it is a lossless line. Okay, it does not matter. So for a motor, the circuit diagram will be what? I will have a EF which will lead angle delta, then I will have this J XS, then I will have VT angle 0. Okay, this will be for a generator. Okay, let me do it for the motor as well. For the motor, what will be the circuit diagram? For the motor, this will be VT angle 0. Then this will be JXS, this will be basically EG angle delta or E angle delta, and remember your delta is negative now. Delta is negative. Okay, please remember delta is less than 0. Okay, because it is a motor, so power will always go from higher angle to lower angle. So yeah, this also like this one more conclusion I forgot to tell, that for reactive power is proportional to delta V, and for active power the conclusion is, for active power, power flow, this is very important for power system, very important. Power will flow, always flow, power will flow from higher angle to lower angle. Power will flow from higher angle to lower angle, that's it. Okay, so now let's understand what is the formula here. Formula will be same for both generator and motor. Power, right, electromagnetic power developed will be EF VT by XS into sine delta. So generally we don't vary EF VT XS, these are constant, we vary delta. So we plot the power with respect to delta. We plot the power with respect to delta. This is the power, right, electromagnetic power developed. So with respect to delta, it is just a sine graph, right? If I just draw the sine graph, okay, okay. So what is the maximum power? So that happens at 90 degree, right? We get the maximum power at delta equals to 90. What is it equals to? EF VT by XS. Right? This is P max. Let me write in short P max. So basically it is just a sine function, right? So this will be equals to P max into sine delta, where my P max is equals to EF VT by XS. Okay, this is what my P max is equals to, correct? Now what I can say is, if there is a load connected, let's say PL load connected, right? So we already know how to calculate the torque and all those things, and in some question I also have taken like stability region, and I have told you that of course it, like, when will it be stable? When it is stable, when the torque is 0. When is torque 0? So I know my power, overall power, right, will be equal to, this is let's say PM, right? PM load is connected, or PL load is connected. So overall power will be, this will be the opposing power and this will be the power that is developed. So overall power will be this opposing power, P developed power minus PL, right? Okay, P minus PL. Same as torque. So if I divide both, or if I multiply both sides by, sorry, if I divide, torque will be equals to uh, power by omega s, yeah. So if I divide both sides by omega s, so this will be P by omega s equals to PE by omega s equals to PL by omega s. So basically the net torque will be equals to the developed torque minus the load torque. And when we reach steady state, when the acceleration is 0, that is T is equals to TL, we reach steady state. This we already know, this we have discussed for motor. So same for generator. When the powers are equal, then we reach steady state. Now here at 2 points it is equal. Which point will be stable? Which point will be stable? Now remember, don't get confused with the previous whatever we had discussed for induction motor, the region of stability for induction motor. Don't get confused here. This is different. Here I am varying delta. Here I am varying delta. There I was varying speed. So I was comparing speed with respect to torque. Remember that graph, right? Torque speed graph. But here I am varying delta. So with respect to delta, which one will be more stable? So I will tell you that this region always will be more stable than delta greater than 90. So delta greater than 90 will be unstable. Now the big question comes, why delta less than 90 is stable and why delta greater than 90 is unstable? That is a bigger question. So for that we have to calculate the slope of this graph. So if I calculate the slope of this graph, dPe del PE upon del delta, okay, with respect to del delta. So if I just calculate, because I assume everything else is constant, if I assume everything else is constant, this will be cos delta, EF VT XS into cos delta. So EF VT into XS into cos delta. Okay, this will be the slope. So if I plot the slope of the graph, right, in the same graph, if I plot the slope, there will be few interesting observations. Okay, so let's assume I don't know anything about stability. If I just plot, so it is cos function, right, cosine function. So cosine function is what? It is just a sine function with a 90-degree lead. That's it. Just a sine function with 90-degree lead. Okay, so this is a this is basically del P, the slope. So let's assume that initially my motor was operating in this region, delta naught. Let's assume this, right? Suddenly if I put a load, so previously this was the developed power and it was equating, right? Load power and developed power was equal. Suddenly if I increase the load, what will happen? Suddenly if I increase the load, the rotor will feel the increased load, right? The rotor will feel the increased load. Same like motor. Let's say I increase the load on the motor. If I increase the load on the motor, what will happen? So if I have two pens, I don't have anything else. Where are the two pens, mate? Okay, just give me 1 second. I'm not able to find. Okay, this also will be fine. So if I connect, so let's assume this is the rotor and this is the stator flux. The angle between the rotor and stator MMF is delta, right? EF and VT, whatever the angle, basically MMF that is delta. So both are rotating with a synchronous speed ns, okay, but the angle is always constant. So hence I am always getting a constant power here. So suddenly if I apply a heavy load on the rotor, what will happen? So the MMF of the stator side will still rotate with speed ns, but if I apply a heavy load, right, So it will stop. It will not stop basically. It will, for a second, it will jerk, and that angle will increase, right? This delta angle will increase, correct? So what I am telling is this is freely rotating. If this is freely rotating, suddenly if I have a opposition here, this will not freely rotate, right? It will rotate, but still with a certain jerk, right? Correct? So same here. Previously these were freely rotating. These two fluxes were freely rotating, and the angle between them was delta. The relative angle between them was delta always. They were freely rotating with speed ns. But suddenly if I apply a load here in the rotor, what will happen? This will stay stuck for a second. This will jerk. This will still rotate, right? So basically if this is ahead, so the stator field is ahead, so this will rotate and the angle delta will increase, right? This will rotate, the stator flux will rotate, rotor will still remain stationary for a second, so delta angle increases. So if delta angle increases, what will happen? It will move upwards. Delta angle is increasing, it will move upwards, right? And sorry, not from here, from here it will move upwards, and this will be the steady state where both of them will be equal, correct? Both of them will be equal. This will be the steady state. That is our aim. But will it stop here? Will it actually stop here? No, it will not stop. Why it will not stop here? So there are two conditions. There are two conditions here. Okay. So when it was at steady state at delta naught, what was happening? My NR was equals to NS. NR was equals to NS, the rotor speed was equals to stator. But as soon as I connect a load there, the rotor stops for a second. The rotor stops for a second, right? So as soon as I increase load, load is increased. So rotor will feel some load, right? If rotor feels some load, NR will become less than NS, and your delta will go to delta naught plus del delta, right? Delta naught will be increased, it will go to delta naught plus del delta, right? Then it will reach this point. Now will it be stable here? Will it be stable here? That is the important question to ask. So here what will happen is, if delta naught is increasing, right? Delta naught is increasing, that means it is trying to, like, still the NR speed is lower, right? So it will reach here, because what is happening? Delta value is increasing, right? So this was rotating with speed ns, and this is stationary for a second, just for a split second, microsecond. Okay. So delta suddenly increased. So I reach this point, but still in this point my NR is less than ns, right? Because for a second it has stopped. So NR is less than ns. So still it will move ahead further. Why? Because to reach steady state, my NR must be equals to ns. How will NR will be equals to ns? For that I need to develop a positive power. Why? Because I need to develop a positive torque. If torque is positive, that means torque on the rotor side is higher, so it will accelerate. So if it wants to accelerate, so NR will go high. NR will go high, right? So I will quickly summarize what is happening. So again I will summarize, again I will explain you this point. So let's say I am at a point delta naught. Okay, again I will summarize. So let's say initially I am at a point delta naught. At this point I am delta naught, right? So if I am at this point delta naught, it is stable. So my PE is equals to PL, it is stable. Suddenly I increased my load, PL, right? PL I increased. So my overall power is equals to P minus PL. Okay. Overall power is PE minus PL. So what do I observe? PE is still lower, right? So it will try to increase, delta will increase, right? Still for a split second, my rotor will stop and stator field will still move. So delta will increase. So delta is increasing. In the part 1, delta is increasing. So delta is increasing, but still my in this case, in this region, PE is still less than PL. So here, right, I'm going here. Okay, I'm going here. So not here. Sorry, I'm going here towards this point. So this point, my PE and PL both will be equal, but still in this region, my PE and PL both still PE is less than PL. So still it is negative. If it is negative, that means what kind of torque are we developing? So my overall torque will be TE minus TL. So still developed torque is negative. That means there is deceleration. Deceleration. Deceleration means my NR will reduce. NR will reduce. Okay, NR will reduce. Right? So still it is actually not getting equals to NS, because at steady state two things needs to happen. At steady state my PE must be equals to PL and my NR must be equals to NS, so that I get a constant torque angle, right? Otherwise this delta angle will keep on changing. If NR and NS are not rotating with the same speed, that delta angle will keep on changing. So in case 2, if I reach in this point, okay, so let me mark the points. Let's say this is point A, this point B, and let's say some other point I have C. Okay, so I will explain about this point. So this is from point A, this I am discussing about point A to B. Now let's discuss about point A, B to C. So from point B to C, what do I notice? From point B to C, what do I notice is delta will still increase, keep on increasing. Now if I am at this point, you will say it has reached steady state because PE is equals to PL. I will say no, still it has not reached steady state because my NR is much lower than NS. So still the delta angle will change. Now what will happen? Delta angle will increase. Why it will increase? Because my NR will try to tend to NS, because my rotor will try to reach steady state, right? So NR will try to reach to NS, right? If NR tries to reach to NS, that means I need acceleration, because NR has to increase. NR has to increase. So for that I need acceleration. Who will provide that acceleration? The motor, right? So basically the torque must be greater than 0, that is my TE must be greater than TL, that means my PE has to be greater than PL. That means basically I have to increase the delta angle. So delta angle will increase. It will go from this point to this point. Now here again another interesting fact happens. Here what happens at point C, at C, as soon as I reach at point C, my NR is equals to NS. But is it steady state now? No, it is still not steady state. Why it is not steady state? Because you see that this time what is happening, my PE is greater than PL, right? So that means I am getting a positive torque. So it will feel like acceleration. So basically what will happen, the rotor will now try to move ahead of the stator. Rotor will now try to move ahead of the stator, right? So previously both were rotating with speed NS, right? Now suddenly a load came, so due to that the rotor for a second it stopped, stator is still rotating, right? So the delta angle increased. Due to that it was developing huge power, but still NR was slow, delta angle was increasing, still the speed was slow. But after this point what happened, that the power developed is more, that means it will develop a positive torque, so it will try to catch up the rotor will try to catch up the stator. So rotor will try to catch up the stator, so the angle will reduce. So it is trying to catch up the stator. So the rotor speed will be higher than the stator now. So NR, not higher, sorry, NR will speed will increase. So slowly this delta angle, relative angle, will slowly reduce because the relative speed is reducing, because NR is tending towards NS. So this will slowly reduce. So slowly again a delta angle will come. Okay, yeah, sorry for the interruption. Like let me explain you again, because like some connection got cut. So I will try to explain the scenario again. So I am at point A initially, delta naught. Okay, and initially what happened is this I increase the load to PL. So what is this PE minus PL? So PE minus PL we had already derived, it is equals to this torque, right? So basically P by omega s. So P by omega s is equals to torque. So if I divide this by omega s on both sides, I will write one more equation. Okay. So what is torque actually is equals to? Torque is equals to moment of inertia into angular acceleration, that is d omega upon dt. So I will write one more equation, that this t is actually equals to moment of inertia of the rotor into angular acceleration, right? Omega by d omega by dt, that's it. Angular acceleration of the rotor by dt. This is equals to my te minus tl, that is 1 by omega s into pe minus pl. Okay, so in the first case, in the first situation, if you see, initially my pl is higher than pe was somewhere around here, this was my p naught, let's say. So initially in the case 1, my PE is lower than PL, so that means this is negative. That means my d omega r will reduce, and that's what I have told you, right? So initially, if you increase the load, the rotor speed will reduce. So basically, what can I say mathematically? Now I am explaining you that d omega r by basically this d omega r by dt is negative, and at steady state, like at zero state, nr was equals to ns, and delta was also steady state p naught equals to pl naught, right? And delta was equals to delta naught. But suddenly at stage 1, I added a load. Okay, suddenly at stage 1, I added a load, so this increase, due to that d omega r by dt will reduce. If d omega r by dt reduce, what happens actually? So this is my rotor nr, and this is my stator ns, and like I'm not drawing the phasor diagram, all those things, mmf, just to give you an intuition that the angle between them is delta, that is constant always. But as your nr is reducing, what will happen? Ns will move with the same speed, but nr will slow down. So what will happen? The angle will increase. So this will be nr, and ns will be somewhere around here. Of course it will not be that drastic, but still delta, this is delta naught, this will increase. Okay, delta will increase. So if delta increases, what happens? Your active power developed will increase. So this difference will slowly reduce. P minus PL will reduce, but still it is negative. If it is negative, still d omega r by dt will be negative. If the slope of speed is negative, that means your speed omega r is reducing. So till this point, omega r will reduce only till the b point. Okay, as I have explained over here as well. Till the b point, there will be d acceleration, nr will reduce. But as soon as I reach after b point, what will happen? This point will not be stable point. Why? Because my nr is still less than ns. Stability means nr, ns both will be same. If why? Because to maintain a constant power angle difference, right? Ns and nr, they have to maintain a constant power angle difference, right? If nr is still lower than ns, what will happen? Still this delta will increase, right? This delta will still increase. This delta will still increase if both of them speed, if both of the speeds are not equal. If both the speeds are not equal, so this is rotating with speed ns and this is rotating with speed nr, this is slower. So relatively, if I keep this stationary, this will just move. So delta is still increasing. So if delta is increasing from b to c, what will happen? This point will still move upwards, right? So if I am now moving upwards, now what will happen? Now my PE will be greater than PL. If it is PE is greater than PL, that means my d omega r by dt is greater than 0. Okay, d omega r by dt is greater than 0. If d omega r by dt is greater than 0, that means my nr speed will increase. It will increase because it has to reduce the like this delta angle, right? It has to reduce. It will increase, and after a certain point, what will happen? It will increase so much, nr will go beyond ns. Nr will go beyond ns. Okay, this will happen. Delta will keep on increase. Nr will go beyond ns. This will happen. Now, as soon as let's say ns is let's say 1500 rpm. Ns is let's say 1500 rpm, and nr is let's say uh, some 2000 rpm, right? So now nr is very higher than ns. Then what will happen? nr is higher than ns, so the rotor is rotating at a faster rate than ns, right? So what can I comment here? This is my nr and this is my ns, okay, and this is my delta. This is rotating with speed 2000 rpm. This is rotating with speed 15. ns is constant, stator field. So what will happen? This is rotating faster, so this will rotate much faster than this. So what will happen? Slowly the delta will reduce. Slowly the delta will reduce. If the delta reduces, what will happen? If the delta reduces, that means what? That means I am coming back from C point. From C point I am coming back, right? So let me mark the C point somewhere here. Okay, otherwise you will get confused. So let's say this is the C point, right? So from C point I will come back basically. From C point I will come back and again reach this position. Again, if I reach this position, what is happening? This time what is happening? Remember, during all of this period, NR is still, during all of this, when C it is coming back. So this is the third portion. When I'm coming back from C to B, during whole of this period, my PE is still greater than PL actually. My PE is still greater than PL. So still my d omega r by dt will be still higher only. If it is higher, speed will increase only. So it will reach to 2500 rpm, somewhere around that. Okay. Again, is this a steady state point? No. Again, at this point, my NR is greater than NS. So it will reduce further. It will reduce further. It will again go back here and it will just keep on oscillating. It will just keep on oscillating. So your question will be, sir, will it not stabilize? No. The answer to that will be no, it will not stabilize. Okay. If no damping is not provided. So this was the ideal case where there was no friction in the motor everywhere. So in the ideal case meaning no friction, okay, and it inherently does not have any damping properties, because cylindrical rotor actually has damping properties, which we will discuss. If no damping, if damping is not present, right, the rotor will just oscillate about point B. So it will just oscillate actually. It will just oscillate about this point B. Okay. So let's assume this point is some angle delta x. Okay. So can you plot your delta x with respect to time? Can you plot your delta x with respect to time? I want to plot my delta x with respect to time. This is time, this is delta of t, right? So what is happening? Initially I was at delta naught. Okay, my lowest point was at delta naught, or whatever was the lowest point, I don't care. Okay, and I will just oscillate about this point. It will be a sine graph, kind of a sine graph only. Okay, and I will oscillate about this point, that will be my delta B basically. Here delta angle will reduce. Why? Because from here, right, it was okay, sorry, not about delta. So my delta was increasing from here to here. This is the point of delta C. This is delta, okay, this is delta, this is not B actually. Okay, some random point, this is actually not x, some random point x here, right? Okay, it is not delta b actually, this will be, let's say this is some delta x, and let's say this is some delta b, this will be delta b, this will be delta c. So there will be some upper limits, lower limit, I don't care about that for now. Okay, so this will be some delta x. Okay, about delta x it will oscillate, and the higher point will be delta c, right? After which it comes down, and the lower point will be delta b. Okay, so it will just oscillate about this point. So if no damping is provided, it is just like a undamped response. It is just like a undamped response. It is just like undamped response. Okay, so what is happening to NR speed in this whole same situation, right? NR, rotor speed. So if you notice one thing, my NR speed is also will oscillate between the speed and NS, right? When NR will be equals to NS, there will be a lower point and there will be upper point. Okay, when, if you notice one thing, when my angle is initially increasing, right, it is going from delta x to delta c. Actually it will initially start from somewhere lower, actually from point A. Okay, point A only it will start, right? Yeah. Okay, let me plot it like this only. It does not matter, I'm just picking a steady state. So when when my delta angle is increasing, what is happening? I know if my delta angle is increasing, that means the relative angle between the rotor and the stator is increasing. That means my NR speed will what? It will reduce. NR speed will reduce. So when this delta angle increases, NR will reduce, because NR is here, right, and NS is here, and I know my relative speed delta is increasing. If delta is increasing, that means NS will, either NR will slow down or NS will fast, but I know NR will slow down. So that means here this will be a phase shifted. It will basically slow down. Okay, so it will slow down, and after a certain stage, it will again increase. When my delta is actually reducing, the stage at which delta starts reducing, my NR will start increasing, right? Self-explanatory. Why? If delta is reducing, that means the relative speed between NR and NS is reducing, right? Delta reduces, that means this angle is reducing, that means NR is increasing its speed, so NR will increase. Okay, so this will be the speed graph basically, and this will keep on oscillating. It will not be stable. If I provide some damping, what will happen? If I am able to provide some damping, right, these oscillations will die out. That is the purpose of damping. That is this phenomenon is actually known as hunting. Okay, this phenomenon is known as hunting, as it's oscillate. That will be resolved in the next lecture. Okay, but today actually we still have not started our topic, that is synchronizing power. I will discuss about the topic. Don't worry a thing, I will discuss about the topic. Okay, so few key observations, right? Let's do few key observations. What are the key observations? The key observations is, if my PE is less than PL. If my PE is less than PL, then what will happen? If my PE is less than PL, then the delta relative angle will always increase. Okay, and two things, my speed, relative speed, right, will reduce. That is my NR, not reduce, sorry, relative speed will increase. That means my NR will reduce. Why? What is PE minus PL? It is proportional to d omega by dt, right? So it is negative, that's why this will happen. This is the first key observation, right? The next key observation is, if PE is greater than PL, then my delta will reduce, right? Because it will try to come back to steady state. Why? P is greater than PL, that means my omega NR is trying to increase. If NR is increased, that means the relative angle will then again reduce, right? Already I have explained this. Okay, I will not explain it over again and again. Okay. So these are the two cases that you have to understand what is happening. So in the first, if I just give you the graph, this graph, can you tell me from what region my developed power is greater or less? So in this region, right, where my delta is actually increasing, this region is the region for which my PE is less than PL, and this whole region where my developed power is reducing, my P is greater than PL. So P is greater than PL here, and P is less than PL here. Okay. So now same for here as well. If you see your NS, like in this region, your NS, rotor speed is reducing. If your rotor speed is reducing, that means what? That means again here, right? When does your rotor speed reduce? When your PE is less than PL. So this region will be PE less than PL, and this region will be my PE greater than PL. Okay. So yeah, so that is the case. These are the few things that you must uh, understand. Okay. So now let's come back to our problem actually. So here we are saying still there is some hope of stability. Like it is trying, if I'm able to provide damping, right, this graph will look like this. If I'm able to provide damping, if damping is provided, the graph of delta of t, like I will provide damping, don't worry. How I will provide that I will discuss in the next lecture. If I provide some damping, what will happen? Let me color this to white. Your delta t, right, will settle basically. So initially it will increase, then due to damping, these oscillations will die down. Ultimately, we will settle at some theta steady state, right? Theta s, so delta s. Okay, we will settle just like a second order underdamped system. Okay, this damping will be provided. Don't worry, this damping will be provided. Okay, so I will come back to this. Before that, we were in a separate topic that which region is stability. So still I have not discussed about this region. This region I have discussed that there is some possibility of stability. If I am able to provide damping, then it will reach a steady state delta. What will happen to the other point? That is what we want to discuss, right? So what will happen if there is some disturbance in the other point? So let us now discuss the case 2. Case 1, where I was in the stable region. Okay, this was the case 1. Case 1, stable region. If I'm at stable region, then this happens, right? Initially your delta naught was here, right, somewhere here. This was my stable region basically. Okay, now let's see if I'm in this region, what will happen. So I will copy this again, and let's assume that I am somewhere here. Let's assume this is my delta naught. Now if I suddenly apply a load, what will happen? If I suddenly apply a load, what will happen? So 0 point. If I'm applying a load here, right? So I see that now what is my difference? So initially at stage 0, PE is equals to PL, and PE is equals to PL, and my NR is equals to NS, right? So suddenly I increase my load, right? So now my PE is greater than PL actually. Sorry, my PE is less than PL. So if P is less than PL, what happens? I know again the same thing, that my d omega r by dt will reduce, sorry, will be negative. That means omega r will reduce. If omega r reduces, that means basically nr reduces. If nr reduces, what happens? Delta will increase. Same thing, right? If here I have nr, here I have ns. So nr, you are saying that it is reducing. nr is reducing. If nr is reducing, this delta will increase. Okay, delta will increase. So delta increases means I will not actually come back to the stable point. I'm not actually reaching the stable point. I am actually coming here. I'm going here. So it is basically unstable point, right? I'm going here. Okay, that is a problem thing, right? What happens? What if I would have done something else? What if I would have reduced the load? So same thing I will do. So this was the case 2 when I am in unstable region. So if I am in unstable region, right, let me assume that initially my delta naught was here and I reduce the load. If I reduce the load, what will happen? If I reduce the load, here if you see that uh, again k0 is same, k0 will be same, that is PL will be equals to PE and NR will be equals to NS. And in once like in the stage 1, what will happen? I have reduced my load. So now at this instant my PE is greater than PL. That means my d omega r by dt is greater than 0. That means my omega r is increasing. If omega r is increasing, that means delta will reduce. If you see here, nr, this is nr ns, right? So basically your ns is rotating with same speed, but nr is increasing. If nr is increasing, this delta will simply reduce. This delta will simply reduce. So delta will reduce. So what can I say? I can say delta is reducing. So if delta is reducing, it will not actually, delta reduces means it will go backwards. It will not go here, right? Delta reduces. So it will go here. So basically from here I can understand that this, right, this region is actually unstable. It is not trying to reach stability. So same thing if you apply, right? Same thing if you apply, if let's say I was somewhere here, if this was my delta naught, right? What would have happened? I will just explain quickly what would have happened. So if this was my delta naught, again at this point PE is greater than PL, so NR will increase, so delta will reduce. So it is actually trying to reach the stable point. Same thing, if I suddenly increase the load, my PE is less than PL, that means NR is reducing. If NR is reducing, my again delta will increase. So I will try to reach the stable point. So that's why this particular region is called as the stable region and this particular region is called as the unstable. So the further on the left hand side I am, that is good for me. So the lower the delta, that is good. But of course I cannot decrease my delta too much because I have to provide output power, right? So that is a conundrum. So that's why a term came known as synchronizing coefficient, and that synchronizing coefficient is given by this equation. Okay, that actually written at the starting. This is known as the synchronizing coefficient. Okay, why is this called as a synchronizing coefficient? Because it tells me how much power it can provide. Basically, if my delta, initially my delta naught is 0, so my synchronizing coefficient is very high, right? Because cos 0 is maximum value. The more closer I reach towards my 90, the synchronizing coefficient reduces. That means I don't have enough power or synchronizing power that can bring the machine back to synchronism. So this synchronizing coefficient actually tells me that how much power I have, how much change in delta P I can do with respect to change in delta basically. so that I can bring my machine back to synchronism. Okay, so this, right, I can write basically there is a term known as PSY. So what is PSY? So PSY is basically synchronizing power coefficient, that is equals to del PE upon del into delta, like change in delta. Okay, so if there is small change in delta, and like if there is huge change in delta, right, I need enough synchronizing power so that I can bring it back to synchronism, right? So that will be provided by this synchronizing power coefficient basically. So this synchronizing power coefficient is, if I give it a change of delta, right, if I give it a change of delta, how much power I will require to bring it back to synchronism, that is what my synchronizing power is, synchronizing power. Because let's say I block the rotor, okay, I hold the rotor, rotor wants to rotate with speed ns, but I hold the rotor. If I hold the rotor, the relative angle will increase. What will happen? The power will increase. So the motor needs to develop a power so that even if I hold, right, even if I hold, the motor will develop enough power so that it will just throw away my hand and it will rotate with speed ns, right? So that is what this synchronizing power tells me, how much power the motor can develop, generate, to bring the motor back into synchronism, or generator, both cases, right? Either bring the motor back into synchronism or the generator. So if you observe a good property about the synchronizing power coefficient, right, that if I'm after this delta naught, what is happening? After this delta naught, the synchronizing power coefficient is negative. That means what? That means it by itself cannot generate any power to bring the machine back into synchronism. It has to take power from the supply or somewhere to bring it back into synchronism. It cannot develop the power on its own. So this PSY is basically power that motor can, for generator it will just be the opposite, motor can generate on its own to bring machine back into synchronism. Okay, okay. So for delta less than 90, PSY will be positive, because with increase in delta, if I increase the rotor angle, basically the deviation, still it is able to generate enough PSY, right? If delta is greater than 90, right, if my operating region is greater than 90, my PSY is negative. What does it mean? Basically it means motor has to take power from supply to maintain synchronism, which will not happen. Okay, which will not happen. Or motor has to take power from the load or supply. This time it has to take power from the load. If I want to bring motor has to take power from the load basically. What do I mean by load? So if I am operating here, right, here, how will I basically bring it to this point? Because this is the stable point, I have to manually do it. So manually manually bring point. So who will bring it? Manually means the load. For a motor, it is the load basically, the mechanical load. So mechanically by hand I have to bring it to that, not by hand, there will be some other means, but I have to bring it back, right? So this is mechanically. So this is what it means, that synchronizing power is negative. Negative means you have to manually do it by yourself, right? The motor will not automatically do it. So from the load, that's what it means, that motor will take power from the load. Okay, so that is what this synchronizing power means. Okay, very very important criteria this is. Okay, we have discussed about the two regions, everything we have discussed. Now let me quickly explain one more thing here, okay, which I was explaining you the hunting part, but I was not able to totally explain it. Okay, so one more thing was missing there about the current. If I want to plot the current, what will be the uh, current basically? How will the current graph look? Okay, that is what I want to plot. So let me do one thing. Let me assume here that it is a motor, right? So if it's a motor, I will have the terminal voltage Vt angle 0 here, and this will be delta basically. This will be EF angle delta, right? Delta will keep on changing because it is negative now. Remember, it has to be negative. That is fine. Okay, EF angle delta, and this is my JXS, right? And this will be my armature current IA. Okay, very important point to note here is that if let's say like my Vt is here, reference, right? So E has to lag basically. So E will be somewhere here, correct? And this is the angle delta. Okay, so of course like this IA into XA will be somewhere here, right? Like I'm just drawing rough triangle, rough phasor. Okay, I'm just drawing rough phasor. So this, remember, this is my EF. Remember, your delta angle is actually changing. So initially what is happening, your delta angle is increasing, right? Increasing. So when your delta angle increases, what will happen? If your delta angle increases, your Vt will be still here, delta has increased. So this will be your EF. One thing you notice that your IA into XS is constant. So basically your magnitude of IA will increase. If delta increases, magnitude of IA increases. Okay, like this I'm doing rough analysis, not exact analysis. Okay, not exact analysis, I'm doing a rough analysis. So your amplitude of IA is increasing when delta is increasing. When delta is reducing, same you will see your amplitude of IA will reduce. Okay, just doing a rough approximate analysis. So can you plot the current? So this is the, like these are the hunting plots. Okay, this will be very very useful in gate, one day they will ask. So one more thing we can plot is the current. Okay, so for plotting the current, what I notice is if delta is increasing, the amplitude of current is increasing. What does amplitude of current mean basically? So I know my current I of t will be a sinusoid function, Im sin omega t, right? But interesting fact is now my amplitude itself, that is Im, is also a function of time. So this will be a function of time, Im of t into sin omega t. Okay, so it is Im of t into sin omega t. So here why Im of t? So Im initially is increasing, then reducing. So this is also a kind of a sine function only, but I don't know frequency. I don't know the frequency of oscillation. Okay, that I don't know. Okay, so yeah, the frequency of oscillations we still have not discussed. So what will be the frequency of oscillation here? That if I want to ask you what will be the frequency of oscillation, can I find out? So frequency of oscillation of delta, right, will be from here, it again starts here. So this is one frequency of oscillation, correct? In one time period basically it oscillates about the stable point only, okay, once only, right? Here okay, here again it will oscillate, and here, sorry, in one time period actually it oscillates twice. So yeah, you can calculate the frequency of oscillation because they can ask a numerical question. So I was thinking if they ask a numerical question, but like what they will do is they will give you this time period, right? So in one time period, how many times am I coming back, right? Only once. Okay. But in case of a current, in case of current, what will happen? So in case of current, if you notice here, so what is the, if this time period is t, right? What is the frequency of oscillation? So frequency of oscillation here for the delta graph, delta of t will be 1 by capital T. Okay, because if you see that I'm starting from this point, again I'm coming back after, sorry, this is not t, sorry, sorry, what I'm doing, this is not t, right? So this is the whole time period basically. Okay, this is t. So if I start from here, again this repeats here. So this is the frequency of oscillation for the graph delta, for the angle delta. But for current it will be something different. So current, right, if I see, initially delta is increasing, right, then again delta is reducing, 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 again from here it starts to increase, increase, again increase, and again reduces. Okay, so in this region what will happen? The current amplitude will increase, right? Again here the current amplitude will reduce, right? Here it goes below steady state delta x. So basically it means that delta will, for a certain second it will be negative, for a certain second it will be leading, for, because this is the stable point. If this is a stable point, it will just oscillate between this vt. Okay, for a certain stage it will be here and here. Okay, it will just oscillate. So basically what will happen, the graph, if I draw the graph, right, how will the graph look? So it will just follow this envelope, it will just follow this envelope. Okay, so here initially my amplitude is increasing, increasing, increasing. Now here, like, what am I explaining? So let's assume that this is some steady state point delta x. Okay, so delta actually reduces after this point, right? After this point. So if it reduces, basically means it is going in the negative direction, opposite direction, right? And if it increases, it is going in this direction. Okay, so in both cases your IA drop, right? If I go more in the negative direction, your IA will increase. Okay, so basically it is reducing, reducing, reducing. Now it is going in the negative direction, so IA will, sorry, what am I telling? It is reducing, reducing, reducing. So here IA reduces. If I'm coming, so this is let's say this is my initial delta. So that if delta is reducing, this drop will reduce. So this drop will reduce. So IA will reduce. But as soon as I cross over my delta x, right, what will happen? Basically, as soon as I will cross over my VT, all this I'm talking about transient. I'm talking about transient. Okay, so it will cross over this point. So here in this situation, what I see, if delta reduces, right, this IA drop will increase. Okay, so the graph will look somewhat like this. Now trust me, this will not be asked actually. This I'm pretty sure this will not be asked. Okay, like even if you are feeling like it is a bit difficult, don't worry. I will explain once more what I'm trying to say. Okay, so basically this will be my envelope here. Okay, this will be my envelope. This will be the positive envelope, and this will be the negative envelope basically. Okay, okay. So what can I say over here? What can I say over here is that, so what are these basically? So remember, these are these oscillations. Okay, because this will be much slower, these oscillations will be much slower because it is mechanical, right? NS is much higher because your frequency of the actual current for ns, right? This is what omega is basically, right? Actual current will be much faster, and this is the envelope. This is called as the envelope basically. So envelope, you draw both sides. You will study this in signals and system. Okay, envelope. So this will be basically the, what is this? This is the uh, frequency of delta of t. This graph is basically the ghost graph of delta of t, right? This graph is basically Im of t, omega x. So this will have some time period t. This will have some time period t. Okay, so now here what will be the current waveform? So I have told you, right, current waveform is sine omega s into t, but this time Im is not, Im is variable, so omega s is much faster, right? So basically in one time period, let's say in one time period, roughly I am telling, in one time period of the rotor oscillations, 10 time periods of 10 cycles of the stator current, because ns is very faster than the speed, like change of delta, right? Delta t is, it changes but not at that fast rate. Okay, so d delta of dt is much slower than ns, right? Change in delta will be much slower than change in, like basically the uh, current speed, or basically ns, right? If ns is less, that is omega s, so omega s is much faster, so basically current will change its direction much faster with respect to delta. So what will happen basically to the current waveform? So current waveform will be something like this. So remember, it will be a sinusoidal, but whose amplitude is changing with respect to what? Delta of t. So if the delta of t is larger, then the amplitude will be higher. So that's why we see, as I am moving at this point, delta of t is larger, so the amplitude is higher. Now why I had to draw this in the negative direction? Because your sinusoid function goes both positive and negative. So of course I have to write down the limits for both positive and negative. So it will just be envelope positive and negative. Okay. So I hope now it is clear why the current waveform like this. Current waveform will be like this. Don't worry, this will not be asked. Okay. In interview they can ask it. Otherwise I just don't want you to get scared by seeing this graph, right? So here one important point to note here, that the current waveform, right, is repeating after t by 2 time. It is not repeating after t. Like of course it is it has a frequency of t by 2. So here, right, what will be the frequency of oscillation? So frequency of oscillation in whole 1t, it is oscillating twice. So frequency of oscillation will be twice than the previous case. So frequency of oscillation because in the previously what was the frequency of oscillation? So I was starting at this point, then again I was coming back at this point. Total time period t. In a whole time period t, I was only coming back to the point once. But here in a whole time period t, because this t is the outside function, that is with respect to delta of t, I am coming back here again and then again here. So twice, right? So that's why frequency of oscillation of current I of t will be equals to 2 times oscillation of delta of t graph basically. Okay, so this is some intuitive thing that can be asked in interview or in some MSQ also, theoretical MSQ this can be asked. So that's it basically for today's lecture. We discussed about synchronizing power, we discussed about hunting. Okay, so intuitively we understood what is synchronizing power, right? So in the next lecture we will understand numerically what does synchronizing power actually means. Also I will talk about all the derivations, right? Everything whatever we discuss, we will talk about that. Like basically the explanations will be there. Today we just intuitively understood what is hunting and what is synchronizing power. Next lecture we will understand numerically. Also we will solve few numericals. So that's it for this lecture. I will see you in the next lecture. Until then, happy learning.